Good afternoon, everyone. I'm Stofan, the John and Adrian Mars Director of the Smithsonian's National Air and Space Museum, and it's my pleasure to welcome you here to today's Asteroid Day program. Before we jump into that, I want to update you on a major project underway to transform our building here on the National Mall. I'm sure you noticed it as you were coming in today, and I want to share a little bit about why it's taking place. This project is really all about providing inspiration to our visitors needed to achieve the next great milestones in aviation and space. Throughout our 7-year renovation program, every one of our galleries either will be updated or absolutely brand new. The reimagined National Air and Space Museum will tell the transformative stories of aviation and space exploration in new ways to new audiences, allowing us to reach further than ever before. But don't worry, during the entire project, we will stay open throughout everything. Even if you see cranes and fencing and all kinds of stuff going on, please keep coming to visit us. While there are big changes underway at the museum, we are dedicated to sharing with the public significant scientific advancements, and today's program does that for the important topic of the potential threat posed by natural impacting objects. Today is the 111th anniversary of the asteroid blast over the Tunguska region of Siberia that I'll be talking about in a little bit. We want to do all we can to try to understand and avoid such an event in the future, particularly if that were to take place above a city. So over the last 5 years, space organizations, schools and universities, and individual scientists around the world have been marking that anniversary with Asteroid Day programming. In fact, in 2016, the United Nations officially designated Asteroid Day as the International Day of Awareness and Education about asteroids. I'm excited to participate this year and look forward to hearing from our amazing presenters today about the latest developments regarding the implications of impact events on Earth and potential ways to mitigate that threat. And I'm going to bring up Jim Zimbelman, a geologist in our Center for Earth and Planetary Studies here at the museum in a second. But first, I'd like to play a video that really talks about why we're doing this renovation at the museum. If we could roll the video, please.
It begins with a spark.
Hey, Jackie, wait for me.
The passion for air and space.
Why don't you take it? You look better on you anyway. Hey, Jackie, remember her?
That passion can grow. Lighting the way forward for a lifetime. And now, with the monumental transformation of the Smithsonian's National Air and Space Museum, this place that has ignited generations of imaginations will be completely reimagined, inside and out. Also, this museum can be even more of what it's always been, a place that gives life to a remarkable past and gives rise to the people who will make history tomorrow. Join us in the mission to transform the National Air and Space Museum. Together, we'll ignite tomorrow.
Well, you've been hearing from Ellen as director. Now I'm going to tell you a little bit about her as a scientist, which is how I've known her for 25 years. She got her bachelor's in geology from the College of William and Mary, a master's and then a PhD from Brown University. And shortly after that, started working at the Jet Propulsion Laboratory in California, where she worked on several different space missions as an active participant and scientist. In 2000, she became vice president of the Proximy Research Organization here in Laytonsville, Maryland. And in 2013, she joined NASA, and shortly after that became the chief scientist working under Administrator Charles Bolden. Then I'm proud to say, as of 2018, she has become the first female director of the Air and Space Museum.
So my job of the speakers today is to give you an overview of impact cratering, how we look at impact craters as planetary scientists, what they tell us about the history of a planet, and a little bit about how they formed. And then some of our subsequent speakers will get into a lot more detail than I'm going to today. So when you look at impact craters, they're a feature that we see on every body that we've visited in the solar system. And so they're really an important feature that we've learned about almost since the beginning. But of course, our real study of impact craters really started right at our own moon, when even from ground-based telescopes, you could see these really large circular features on the moon. And early scientists, and then up until the time we went to the moon, people said, well, how on earth did those large circular features form? And even up through the Apollo program, there were a lot of arguments until we could really start getting close-up images of the moon from the early Surveyor spacecraft, and then a lot more detail from Apollo. There was a big debate. Could these be giant volcanoes on the moon, or were they formed by some other process? And scientists right away started saying, well, what if something hit? It would obviously create a big hole. And so could those features actually have been caused by something, and that something likely being a comet or an asteroid hitting the surface of a planet and creating these giant holes? And as we're going to hear about today, as we saw them on the moon, we started looking around a lot closer on the Earth at features here and realizing, okay, not only if they happened on the moon, they certainly happened right here on the Earth. So as we got closer and closer to the moon, we realized that these large circular features really didn't have a lot of the characteristic surface features that a volcano does. And so there was a consensus in the scientific community that yes, these were impact craters. And as we studied the moon and got more and more spacecraft data of the lunar surface, we were able to study the morphology, again, the shapes of these features in much more detail, which helped us to understand better and better how they formed. This is a central peak, which some of the craters have these giant peaks inside of them. And you can see this peak is actually 2 kilometers high and 15 kilometers wide. And now remember, when you're looking at something like the moon, unlike the Earth, there's obviously no water on the moon, there's no atmosphere. So these are uneroded features. This is really important as we have gone on to study impact morphology, is having these features on other planets where they're in pristine condition. They haven't been washed away by rain, they haven't been changed by plate tectonics the way everything here is on the Earth. We can actually study these features and say, wow, what would have the early Earth looked like? And how can we use that information to really understand what the effects of impacts have been throughout Earth history? So being able to see this detailed shapes in their very, very pristine state has been very important in geology. And you can see, this is again Tycho crater. It's an amazingly complex crater. You can see the whole crater there, that central peak in the middle, and then the location of it there on the bottom right. One of the things we realized as we looked at craters across the lunar surface is they tend to have a set shape. Bigger and bigger and bigger. The shape is more and more and more complicated. They start out as just pits on the surface. Then you go to what's called a simple crater, where it's just a bowl-shaped form. to craters like Tycho that I just showed you that have central peaks. That's called a complex crater. Then in the next form, as they get even bigger, and you can see that Schrödinger crater, which is about 300 kilometers across, so that's quite a large feature, that they have not just a central peak, but they'll have a ring. So they'll have two rings, not just the outer rim of the crater, all the way to extremely large impact basins like Oriental on the moon. That's over 900 kilometers across, where the central peak is now gone and you can have rings. Now, if you want to think of impact cratering really simplistically, think about that multi-ring shape, and then think about what happens when you throw a rock into a pond and it creates a whole series of concentric rings. All right, that's not so different from what's happening here. And believe it or not, scientists have done lots of experiments here on the Earth, starting from literally dropping rocks and seeing the different shapes that can form in different types of material, to actually, we have a high velocity gun out at NASA Ames Research Center in California, where they actually try to recreate this extremely energetic impact process by shooting things at other things. So that's kind of a fun career for kids if you think about it. But through that, again, if you go back to this, and I'm going to bring this up, and I know Tom Jones, who he and I wrote a book and a magazine, we've written a couple things together, on the reason we go out and study the planets. We're always bringing that information back here to Earth to better understand our own planet. So when we do these models by using the high velocity impact gun, when we go to the moon and really try to understand these different craters, it's always bringing that back to the Earth and saying, how can we learn about Earth's history by looking at other planets? But of course, it's not just Earth's history, and you're going to hear a lot more about this today. This is not history, like, okay, asteroids and comets have hit the Earth in the past, and it's never going to happen again. Sorry, that's not the case. And we know that well from just a few years ago when we had the over Chelyabinsk, which is in Siberia. You can see this from a lot of dash cam videos. It was captured as this impactor, probably a small chunk of an asteroid, came into the atmosphere, burned up in the atmosphere, but because it was big enough, it created a giant blast. It left this impressive trail in the air. When it exploded, it broke windows all across Chelyabinsk, scared an awful lot of people, an awful lot, wondering what on earth was happening. And scientists have actually been able to recover fragments of the Chelyabinsk meteorite and bring it back. So this, and analyze from what kind of an asteroid it came from. So having these things happen on Earth, it's a reminder to us that we really need to understand these things quite well to be able to really protect against them in the future, which is again the theme of today's program. Now, I mentioned earlier that this is the 111th anniversary of the Tunguska event, again over Siberia. Don't think that Siberia is being picked on, but there have been a number of events over Siberia. You can see that when this happened, the area was actually pretty sparsely populated, but there actually were people living in the area. And this was an incredible, you can see from the scale on that, this was an incredibly energetic event that had affected a very large region. And what happened was it knocked down the explosion, which occurred in the air, sort of like Chelyabinsk, but on a much bigger scale. It knocked down trees over hundreds of acres with the power of this blast. So just think of the power that's coming, the energy from this thing coming streaking into the atmosphere. It explodes above the surface because there's too much pressure coming from the atmosphere. It causes the hot rock to explode and creates this devastation. Now remember, this is a body that's too small, that those atmospheric forces don't cause it to break up. If the body were any bigger, the actual fragment of an asteroid or an actual asteroid could make it all the way to the surface. So what we call this, and that wasn't on that chart of different sizes of impact craters that I showed you, is called an airburst. So again, the atmospheric pressure causes the impactor to break up, but there's a giant explosion, the shock waves coming through the atmosphere, again, strong enough to knock down hundreds of acres of trees. Now, we saw these really clearly. We first started, a bunch of us here worked on the Magellan mission to Venus, And when we were looking at that data, which you can see on the left of this slide, we kept seeing these funny shadowy things, these sort of dark splotches with a bright rim around them. Venus has a very, very dense atmosphere, so it's very hard for bodies coming in, whether it's a fragment of a comet or an asteroid, it's even harder for them to reach the surface, and they have a tendency to explode above the surface. And what it does is it pulverizes about the upper meter or so of the surface, which produces those dark shadows in the radar data that you see on the left. Now again, our concern is, and why we're talking about this today, is this same thing could happen over a major US city, a major city anywhere in the world. And okay, Tunguska was just over a forested region, but this is a lot more serious if it happened over a city. Now we do see impact craters on the Earth, and you're going to see a lot more of this today. This is Meteor Crater in Arizona. And when the impactor actually makes it to the ground to form a crater, it's 100 times the force of the Hiroshima bomb. And Meteor Crater is actually a very small impact crater. Huge amount of energy when these things form. Now, right here in our region, we actually also have an ancient impact site that wasn't recognized for quite a long time. The Chesapeake Bay was actually formed, the structure around the Chesapeake Bay, and you can see the outlines of it, and it's one of these multi-ring impact craters that I showed you an image of from the moon. And we know this now from both the gravity data that we have taken over the Chesapeake Bay, as well as deformation in the rock layers that we can measure. So what scientists do when they think, okay, there was an actual impact in this spot, is we create a lot of models to say, what was the size of the incoming body that would have affected this? How deep into the Earth did that power actually go and excavate? And then can we use that information to understand what the effects on the atmosphere would have been at the time? Now, you guys have also all heard of a very famous impact, and I hope you all how many people here today have had time to get over to Deep Time over at the Natural History Museum? You guys have to go over there. It's really cool. It's really cool. It's a great new exhibit. I really urge people to go. That, of course, you're going to see a lot of dinosaur fossils at Deep Time over at Natural History. A lot of those dinosaurs, obviously dinosaurs went extinct after the impact that left the Chicxulub crater, which is in the Yucatan Peninsula in Mexico. And this kind of giant impact that we even think is probably responsible for the formation of the moon can do huge damage to the planet. Now, the good news is really large-sized bodies, like the one that would have created the moon from the Earth, and even probably that created the Chicxulub crater, those bodies are in very low abundance. We really worry about smaller things, sort of under 10 kilometers. But again, you're going to on their surface. And as you can see, come in all shapes. This is the Vesta asteroid imaged by the Dawn spacecraft. So these things, which are made of lots of different combinations, some are stony, some are metallic, and what they're made of is also important too, because that will also affect the formation of an impact crater. We actually had a spacecraft called Deep Impact that impacted into Comet Tempel 1, giving us even more information about the structure and strength of these bodies, which helps us model their potential impact on the Earth. We even had the ability on the moon to impact something into the moon and watch it form, which helps give us even more information. We've done this several times. This is just an example from the Apollo 14. One of the stages impacted onto the moon, and you can see the little bright crater there that formed when that impacted on. Again, it allows us to model it. We know what it was, how big it was, how much it weighed, so we can model the process. We also had the ability a couple decades ago in '94 when the comet Shoemaker-Levy, which was a series of fragments of a comet that you can see there at the bottom of the slide, impacted into Jupiter. And we watched that happen with the Hubble Space Telescope and could make a model of it. Now, I've been talking about the moon, but again, craters have formed on every planet. And when you look at somewhere like Mars, which this is topographic data of Mars, even you can look at this right away. Anybody can look at this and say, wow, there's a lot of craters on the bottom half of Mars and hardly any at the top. Why is that? Well, it turned out about 3.5 billion years ago, the whole top half of Mars was covered in water. So you don't see all the impact craters that we see in the southern hemisphere of Mars. So now we can start using impact craters to understand the geologic history of a planet. This is a recent crater that formed just a few years ago on Mars. So craters are still forming. Again, this is why we're talking about it. This is why we worry about it. This is a relatively recent crater that formed on Mars. Craters are on Venus, but Venus has a lot fewer craters, which tells us that Venus is a much younger planet. It's much more geologically active, so geology is covering up the craters and we don't see them all over the surface. We even see craters out in the outer solar system. This is Ganymede, one of the moons of Jupiter. And you can see because that satellite, Ganymede, is actually made of water ice, not rock, the craters actually take a very different form. And that helps us, again, understand the physics of the process that forms craters. This is a crater called Minerva. It's on Saturn's satellite Titan. And you can see, even though it's impacting into water ice, it's formed these ring structures, still obeying that basic sequence of how craters formed. Now, as you can see, and this is my last slide, and then we'll have time for some questions, craters have this, impacts into the Earth, like I talked about at the Cretaceous-Tertiary boundary, where we had the extinction of the dinosaurs, most life on Earth. We get these mass extinctions on Earth from a lot of different causes, but it's clear that impact of an asteroid or a comet into the surface of the Earth can have devastating effects of life on Earth. Though I want to say, at the end of my talk here, we think, in a new mass extinction here in the Anthropocene, the time we live now. And it's not being caused by any of the factors you see here. It's actually caused by humans' effect on the climate, the fact that we spread all over the Earth, we take diseases and everything all over the place. So while we worry about asteroids, remember that climate is something you can have an impact on every day in the choices you make. We have time for a few questions. Questions? Yes?
You mentioned that crash, was it a rocket into the moon?
Yes. We've done it a couple times.
Was there a measurable echo detected?
That's a great question. So when you crash something into the surface, the whole planet will shake. You'd actually get a seismic event. If you had seismometers all over the surface and you impacted something into the surface of Mars or the moon or any other body, you should be able to measure that on very capable seismometers. Now, I think Apollo 14, I'm actually not sure if we did detect it. Jim is telling me we did, because at that point we had seismometers that were active on the moon that the Apollo astronauts had deployed. We don't have seismometers now on the moon, so we can't monitor it. We have a seismometer on Mars, though, so if there's an impact on Mars that's big enough, we'll catch it.
Thank you.
Mm-hmm. Yeah?
Would there be any seismic activity on gas giants? Because you said we could take a reading from anywhere on any planet.
Yeah, seismic activity on gas giants. The problem is, for seismic activity, you actually need a solid body. And on gas giants, we could do it on their satellites, which have this water ice crust, and we could actually measure. And in fact, there's a new mission that just got selected last week called the Dragonfly mission that's going to Titan. Woohoo for Dragonfly. I'm on the science team. We're pretty excited. We actually have a seismometer that's going to go out to Titan. It's part of the Dragonfly payload. So we can measure it on the satellites. But those icy bodies are gas giants, and if you're interested, the whole structure of what a gas giant looks like where there are actual solid body at the center of a gas giant, would that have seismic activity? But we're getting some really interesting results from the Juno mission to Jupiter that suggest there may be some liquid metal layers higher in Jupiter's atmosphere than we had thought. And we now know that the layering on Jupiter is way weirder than we ever thought it would be. Okay, I can take one last question.
I noticed that one of the asteroids, the chemical composition was nickel iron. I was curious about what the most common compositions and what effect that has on morphology.
I didn't hear how does it is nickel iron, so how does it compare to?
So what are the most common compositions? How does that
Yeah, great question. So composition of asteroids, and we have experts that are coming up next, so I'm going to largely defer this to Tom Jones, who's an asteroid expert. But they go all the way from, just think of what our planet is like, where we have rocky upper layers, then we have, as you go, we have a metallic core. So asteroids actually reflect that same. There's a lot of asteroids that are stony, and then there's very fewer that are actually metallic, and we have a mission called Psyche that's in development right now that's going to go to a metal asteroid. Okay, Jim Zimbelman's going to take over. Thank you all.
Mike, there we go. Sorry about that. We'll start again. The next speaker is going to be Tom Jones, and he has his own mic, by the way. Tom got his bachelor's degree from the U.S. Air Force Academy and then piloted B-52D strategic bombers for several years. After that, though, he got his PhD in planetary sciences from the University of Arizona, where he studied asteroids. So as a scientist, he knows these rocks. But in 1990, he was selected by NASA as an astronaut. He flew 4 shuttle missions, the last of which was to the International Space Station. And during those 4 flights, he logged 53 days in space, including 19 hours during 3 spacewalks. His website says he is a scientist, speaker, author, and consultant. Here's Tom Jones.
Thank you. How's this microphone working? Okay, good. Welcome everybody to Asteroid Day here at the National Air and Space Museum, and to everybody who's watching around the world on the live stream, welcome to all of you. It's a pleasure to be up here with Ellen, the director here, and all the great colleagues on our panel today. One thing I learned as an astronaut was that teamwork can help you accomplish great things, and with the kind of team members that we have here at the museum and at NASA and the various contractor and laboratory teams that we've got around the country, we actually can do something about the Earth being hit by asteroids in the future. And we live in an era, it's called the space age, where we have the skills and the teamwork to actually prevent the Earth from being struck by a dangerous asteroid in the future. But whether that actually happens is up to us. So the teamwork is possible, but we actually have to get behind that team effort, and I'm going to talk to you about some ways that we can do that. Okay? So one part of the astronaut's perspective about this asteroid impact process is that it's a topic that's on the public's mind as part of NASA and its space effort here in the US. Well, a recent poll in May of this year showed that 63% of the public in a poll of over 1,000 adults said that one of the most important things NASA could do would be to monitor comets and asteroids to prevent a future impact on the Earth. And they gave it higher priority in NASA's agenda than returning astronauts to the moon or going on to Mars one day. I happen to think that if we go to the planets with human explorers, we're going to learn a lot about how to prevent the Earth being struck by asteroids and comets. But it just shows that the public's interested in this topic of how we can use our space skills and teamwork to prevent a future asteroid impact. And it's really possible for us to do that. So I'm a scientist who studied asteroids, and I'm an astronaut who's been in orbit and looked out at the cosmos. And most importantly for this discussion today, I've looked down at our planet and seen some of the evidence of that cosmic bombardment process that Ellen talked about. So I'm going to talk to you about my astronaut perspective from orbit, looking down at the Earth and the impact scars here. Talk about how it's a global phenomenon. It doesn't just affect Siberia or the United States. It's a global phenomenon that we all have to face up to and cooperate in solving. And then we're going to talk about how that international response can help us prevent a future damaging impact. Now, this month coming up, July, is the 50th anniversary of the Apollo moon landing that occurred 50 years ago in July of 1969. And this is a shot from Apollo 11, from the astronauts returning from the moon, and they saw the full face of the moon and all those impact craters that we've just been talking about. And so they saw up close, on the surface, leaving the moon, coming back to Earth, how damaged, how battered our closest neighbor in space has been. And of course, the moon is our companion planet, so everything that's happened on the moon has happened here on Earth. And yet we don't see those asteroid scars like this one on the surface of the moon here on the Earth. Only a few examples on the Earth are fresh craters like this one, Shorty, on the Taurus-Littrow region of the moon. And that's because, you know, the Earth is an active body. It's got plate tectonics. It's got erosion going on under its atmosphere, constantly renewing and destroying the surface. And so the record of these impact scars has been wiped out on the Earth. And fortunately, we have tape recorders, like the moon and like the other planetary bodies in the solar system, to tell us about this cosmic bombardment process. If you look at the graphic here, you see the inner solar system in this little video showing the inner planets at the center, the Earth, the sun at the center of the Earth, Mercury, Venus, and Mars circulating around. Mars is the red orbit, sort of at the top third of the screen. And then beyond Mars is that big green belt of objects called the asteroid belt, the main asteroid belt. That's where there's over 500,000 known asteroids in our catalogs today. Between Mars and Jupiter are the remnants of the leftovers of a planet that tried to form there 4.6 billion years ago. It never got assembled because of Jupiter's massive gravity. That's the main asteroid belt in green. But because of Jupiter's continuing gravitational influence in that region and collisions between bodies in the asteroid belt, some of those fragments of the asteroid belt get pushed into the inner solar system. And we have millions of small objects that penetrate all the way towards the sun, and they get run into by the terrestrial planets, including the Earth. And so these near-Earth objects, some comets, mostly asteroids, are the population that concern us and presents to us the bombardment hazard from space that we have to worry about today. Now we have telescopes now that can look for asteroids, and Lindley Johnson here from NASA is going to tell us all about that program. One example of this observing program is this object 2012 TC4 that flew by the Earth in the fall of 2017, and our tracking cameras monitored this asteroid as it flew within 30,000 miles of the Earth. It's only about 45 feet across. It missed us by 30,000 miles, but we get regular detections like this of objects that come close to the Earth. In fact, in the course of a year, there's probably a couple of dozen asteroids that come within us and the moon, fly between the Earth and the moon, and they get picked up by our cameras. And there are a lot that don't get picked up by our telescopes and cameras as well. So it's a constant process of the Earth flying through a shooting gallery of objects that may run into us someday. Here's another example of NASA data of a radar image of 2003 SD220. We have these really sexy names for these objects. This is a very elongated cigar-shaped asteroid that came close back in 2018. So if we're lucky, we get the shape of an asteroid if it comes close enough for our radar telescopes to detect it. Usually we just get a bright white dot going across the sky. And that's sufficient to determine the orbit of the object and predict whether it's going to strike the Earth in the future. Now we know from Ellen's talk how often the Earth has been struck in the past by big asteroids and comets. This is the biggest one that exists on Earth today, the Vredefort structure in South Africa. As you can see, it's 300 kilometers in diameter. Happened a long time ago, only about halfway back through the Earth's geologic history. But the multi-ring structure of this body is still visible on the continent of Africa. And you can see these from a spacecraft. I've looked down on many of my 53 nights in space. After the work was done and it was time for bed, I could peer out the window with a camera and take a look at some of these objects that scarred the Earth in the past. Here's the Manicouagan impact crater in Canada, up in Quebec province, 214 million years old. But it's on one of the ancient parts of the North American continent, so it's still there for us to see, despite the ice ages that have erased most of the topography of this crater up in Quebec. And then on my first couple of flights, working with Ellen Stofan here in the Jet Propulsion Lab team, we flew an advanced imaging radar, and over the Sahara Desert in the country of Chad, we found this Arunga impact structure buried beneath the sands of the Sahara. And it peeks out above the sands. You can actually see it with your eyes from space. But the radar removed the sand cover and showed us the geologic structure of this body. So another impact scar reminding us that the Earth is a target of these near-Earth objects. Has been in the past, will be in the future. Who's been to Meteor Crater in Arizona? It's a great vacation destination when you're on your swing to the Grand Canyon. It's only a couple of hours away from there, near Flagstaff, Arizona. This is the Barringer crater, one of the freshest impact craters on the planet. It happened about 50,000 years ago. You can see it here from orbit in the shuttle photograph. When you get up close to it, it happened 50,000 years ago in a region that's been a desert ever since, so the erosion processes on the Earth have not wiped it out yet. Instead, you can see this fine example. It's about a mile across of an impact scar. About a 20 megaton blast created this impact structure on the desert. And I've been there with students, geology students, and we can go down to the bottom of the crater and see the layers of the Earth's bedrock that have been turned over and blasted, peeled apart by this impact 50,000 years ago. So it's a great laboratory. The Apollo astronauts trained at this site for their moonwalks during the Apollo missions. Now, if you look around the Earth, geologists know of about 195 meteorite craters on the planet today. There are many more probably undiscovered on the ocean floor, and many more, of course, that have been destroyed by erosion. So we do have that impact record to look back at, tell us about the process of being struck by an asteroid or comet. But what this tells us is that this is a phenomenon that's occurred many times in the past, and if we don't do anything about it, it's going to occur in the future. 100% certainty that we're going to be struck by a future dangerous object, unless we use our skills and our teamwork to prevent it. NASA's got this wonderful chart here that they provide on their CNEOS website, and it's a map of fireballs in the atmosphere seen by Air Force sensors looking down at the Earth. And their infrared sensors detect these asteroid explosions in the atmosphere. This map goes from, 2015 till 2020. And Chelyabinsk shows up there as the big red dot over Siberia. That's the most energetic one that we've seen. Lindley's going to talk some more about this kind of sensor work that tells us about the frequency of asteroid impacts on the Earth. My point here is that these impacts happen all over the world, 24/7, round the clock, around the course of the year. So we're being struck by asteroids, comet fragments, but fortunately our atmosphere filters most of them out. But it's a global hazard that we have to confront. No matter where you are around the globe, you can experience a fireball like this if you're up late at night. Here's one in Arizona in 2016. That got the attention of these drivers on the interstate. Then another one in South Africa last year, a fireball lit up the skies. June 3rd, 2018, and this was an asteroid fragment that lit up the night sky. More importantly, asteroids like this can be detected in advance. We've detected 2 or 3 of these small impactors before they hit the atmosphere, and then we've seen the fireballs, and then you can also note meteorite teams go out and pick up the fragments on the ground. Talked about Chelyabinsk, February 15th of 2013, when we had a half a megaton explosion over this Russian city. It was a timely reminder of how we can work together to detect these asteroids in advance and then work together to prevent them. In fact, that day I was at the United Nations with Lindley. We were there speaking about the asteroid defense problem, planetary defense, when we got word that Chelyabinsk had been struck by the blast wave from an airburst over the city. And there wasn't a more graphic way to remind the delegates to the United Nations about the importance of this topic and working together. Here's a graphic that shows you the size of the body that exploded over Chelyabinsk in the lower right corner. And that same day, by coincidence, another asteroid, DA14, about 45 meters across, was going to miss the Earth by just about 25,000 miles. Now, we knew it was going to miss the Earth. There was no chance that it would hit us. But had DA14 struck a city, it would not have just created a blast wave that shattered windows. It would have wiped out that city. And that's a reminder of the kind of shooting gallery that we orbit through, that we have to pay attention to. We have to catalog the dangerous asteroids that might be coming our way and then give ourselves enough warning time to prevent that impact from happening with our space skills. So it's a global hazard. We need a global response. I'm a member of the Association of Space Explorers, the Planetary Society, the professional global group of astronauts and cosmonauts. And we get together for a meeting every year. One of the topics that we discuss is environmental stewardship of our planet. And one of the ways that we can preserve our environment is to keep this planet from being struck by a dangerous asteroid in the future. And the Association of Space Explorers, this astronaut society, is just one of the small players among the many, like NASA, like the nation states of the world, that talk about this topic at the United Nations. And we've been fortunate enough to participate in the discussions over the last 10 or 15 years. There was an asteroid that struck the Earth, 2018 LA, back in June of 2018. And the initial track from our telescopes and the computers predicting the impact point showed that it could strike anywhere from Australia or Indonesia there all the way across South Africa. Couldn't narrow it down until very close to its impact with the Earth. So you can see it's a global hazard. This was a small asteroid the size of a pickup truck. It wasn't going to destroy a city, but it was going to provide a graphic demonstration of our tracking and warning abilities. And here's a better map of the possible impact points that this asteroid might fall upon the Earth. In the end, it actually landed over South Africa. However, it wasn't until a few hours before impact that we got the data that we needed to pin down the impact point. So again, it's a global hazard. It can affect many countries across the world once we make a detection of a hazardous asteroid. And should we know in advance about an asteroid that's going to strike the Earth, we can do something about it. We can use a variety of technical means. We're going to hear about that from Lena and from Lindley about how we can divert an asteroid. But if you want to prevent an impact on the Earth, the red explosions there, and push the asteroid so that it misses the Earth to the left or the right, you can see that in doing that pushing, you're going to make it drag the impact point across different countries of the world. So together, we have to decide in advance of how we're going to solve this problem. If I knew about an asteroid that was going to land on Washington, D.C., I'd want to push it off that target and move it off the edge of the Earth entirely. But if in the process we navigated that asteroid across Paris, the French would be a little upset about that. Because what if something interrupted the process and we had to have a new impact point over France? So together as a global community, we have to work together to make plans in advance on how we're going to decide which way to push the asteroid, how we're going to do it most effectively, how we're going to fund that effort. That's where international discussions come in, okay? So we discussed these problems at the United Nations. Over the last 10 or 15 years, I've been at several of these bodies, several of these meetings in Vienna, talking about the progress there. The Association of Space Explorers wrote a report, Asteroid Threats. We suggested some warning and advisory groups that the UN might adopt. And it turns out that after we wrote this report in 2009, some of our suggestions were rolled into a UN-endorsed plan for dealing with future asteroid impacts. And there's an International Asteroid Warning Network in the lower left, a Space Missions Planning and Advisory Group that plans the technical means to divert an asteroid. And this is the United Nations map, if you will, the planning map of how we would warn the world in case of an asteroid impact. And agencies like NASA, other space agencies around the world, and other countries that are interested in this problem have collaborated in adopting this plan. So we've come a long way since 2009. We've adopted Asteroid Day starting in 2016. Some of my astronaut friends and I submitted a suggestion to the UN that they adopt Asteroid Day as an international event, and that was approved. So we're keenly aware, astronauts around the world, space agencies, our team members around the world, about how we can work together to prevent an impact. And that comes from warning capabilities like future space telescopes we're going to hear about, comes from space missions like the DART mission that Lena's going to talk about to deflect an asteroid and prove that we can do this for real. That teamwork is going to be essential towards preventing a future asteroid impact. And I'm going to wrap up with just a couple of thoughts here about asteroid exploration. We have spacecraft visiting asteroids right now around the solar system. We've got a Japanese craft called Hayabusa, another one called OSIRIS-REx from NASA, exploring individual asteroids. When I was an astronaut on the space station, I was doing a spacewalk when I heard over my radio headset that we had actually landed our first spacecraft on the surface of an asteroid. It was the asteroid Eros, and the Near-Shoemaker spacecraft had touched down there. So I've heard about robot probes going to space objects while I've been a space object myself. I'd like to think that in the 21st century, we're not only going to prevent future asteroid impacts, but we're going to explore with human beings the rest of the small bodies in the solar system, take advantage of the resources that they offer us, use them as stepping stones to Mars. And at the same time, we're going to reap the major benefit from space exploration in the 21st century, and that is to stop a future asteroid impact on this planet. So I'll leave it there and invite you to ask any questions you've got. Thank you very much. If you got a question, come on up to the microphone, and we'll be glad to entertain a few. Got a couple of minutes here. You can check out the asteroidday.org website, asteroidday.org. Tells you more about the Asteroid Day educational effort. We've also got my Association of Space Explorers website. You can check that out, space-explorers.org. And we'd be happy to hear from you via that means as well. We're also taking questions on Facebook Live from the Air and Space Museum site. So chime in with your questions from the internet if you've got any. Anybody else have a question? Yes, sir. Can you come up to the microphone, please? That way everybody can hear your question.
I'm not really sure the year it's supposed to happen, but I think it's called Apophis.
Apophis, yeah.
Right. So I wanted to know if you could speak to that. The keyhole, if it's going to pass through the keyhole, I think in 2020 and then around in 2036, or something like that.
So our questioner here has an interest in the asteroid Apophis. It's a medium-sized near-Earth object, a few hundred meters across. It's going to approach the Earth very closely in 2029, and we know from our tracking information that there's no chance it's going to strike us that year. It's going to come very close within the orbit of the geosynchronous communication satellites that are out there around the Earth. So it's going to be a near miss. It's going to come back 7 years later, and the current tracking information tells us that it's not going to strike us then either. But there is the possibility when any object comes close to the Earth that the Earth's gravity will bend its path such that the next time it comes around the sun, it might actually return and strike the Earth. And that's called a gravitational keyhole. If the object misses that gravitational bad spot, I wouldn't call it a sweet spot. If it misses it, it's not going to come back and strike us. If it goes right through that gravitational bad luck spot, it could be bent in such a way that the orbit will carry it into an impact. It's not going to happen with Apophis, but it's going to be the most spectacular asteroid flyby in 2029. You want to be in the eastern Atlantic Ocean or on Europe's doorstep to watch that flyby. You'll be able to see it with the naked eye going across the sky. Anybody else? Yes?
When do you think the next asteroid's going to come?
When do I think the next asteroid is going to come? Well, Lindley Johnson here works for the NASA folks who track all the known asteroids. None of them are on a collision course with the Earth. But the problem is we don't know about all the asteroids. We haven't found them all yet. So part of our job is to discover these hundreds of thousands of asteroids that could destroy a city here someday if they happen to be on the wrong orbit. And once we know that they're out there and they're coming our way, then we can put together a space mission, which we're going to hear about, to deflect a future collision. So you don't have to lose any sleep about this, but it's all about teamwork. It's all about bringing the countries of the world together to work on it together. Thank you. Go ahead.
I hope this is not too dark, but have there been estimates of the absolute worst place an asteroid can strike Earth? For example, if it strikes the desert, could it throw a lot of sand into the atmosphere? There has to have been some studies of the absolute worst place that an asteroid can.
Yeah, what bad things can happen from an asteroid impact and how bad can it get? So, it's all about transforming the asteroid's kinetic energy of its motion around the sun into heat and thermal energy. When it strikes the Earth and stops instantly, all of that kinetic energy is transformed into heat and light, and that blast power, that released energy, creates a crater, throws debris into the atmosphere. So if it's a big asteroid, it could throw enough dust into the atmosphere, for example, to shut down photosynthesis and stop the growing season. And a lot of us would starve in that year of a bad asteroid impact. If it's a smaller asteroid, the blast power alone, like we saw at Chelyabinsk in 2013, could actually damage or destroy the buildings in a city just from the blast wave alone. So it depends on the size of the asteroid, it depends on where it strikes and what target material it hits. Fortunately for us, 3/4 of the world is ocean, and nobody's living there, and probably the tsunami would strike the shoreline, but if it's not a big asteroid, that's not really a big problem. If it strikes on land, only 4% of the Earth's land area is urban, with lots of people living close together. So chances are, again, it's going to land in Siberia, in the trackless wastes of Antarctica, someplace like that. So most of the time, not a problem. But we don't want to rely on just good luck to protect our planet and our species. We actually can do something about it. Thanks for your question. Over to Jim.
Well, our next speaker is one that Tom referred to. Lindley Johnson has one of the coolest titles I can think of, Planetary Defense Officer for NASA. He got his bachelor's in astronomy from the University of Kansas, after which he served for 23 years in active duty in the Air Force. Following that, he got a master's in engineering management from the University of Southern California, and now he serves in the Planetary Defense Coordination Office at NASA.
Jim, Well, thank you. I'm excited to be here today to talk to you about what a small percentage of the American taxpayers' dollars get spent for at NASA, and that is for trying to detect any potential hazard to the Earth from an asteroid or comet and be able to do something about it. So at NASA, every day is an asteroid day, and I'll talk to you about that a little bit more here in my presentation. I head up the Planetary Defense Coordination Office at NASA, and we're tasked with the job of detecting whether there is going to be any significant impact to the Earth by an asteroid or a comet, and being able to assess, tell our leadership and decision makers what the effects could be, how bad could it be. Now, the Earth gets hit every day with small stuff, as you've seen in some of the previous presentations. The Earth's atmosphere does a very good job of protecting us from most of that. But if an object the size larger than Chelyabinsk or so were to impact, it could be a serious day for some part on Earth. And if the object is big enough, half a kilometer or so in size, well, that could be climate change in an afternoon. So we do work to be able to model and assess what could happen from various sizes of asteroids of various compositions and where they might impact on the Earth. And also work both with other U.S. government agencies. This is more than just a NASA issue. If we were to be faced with such an impact, it would be something the entire U.S. government would have to react to. And also with our international counterparts, colleagues in other countries and space agencies, to figure out, develop strategies about what we would do about such an event. So what are we talking about? We've talked about near-Earth objects, near-Earth asteroids. We're seeking to find all of the near-Earth objects, that's asteroids and comets, that come within technically 1.3 astronomical units of the Sun. Well, that's about 130 million miles from the Sun. It's not based upon where the Earth is at all. It's how close do they get to the Sun. That brings them into the inner solar system and into trajectories that then could come close to the Earth and impact the Earth. So we have to survey this whole part of the inner solar system to find these objects. What we're really looking for are those that are a potential hazard to the Earth, and those are objects that will come within 5 million miles of Earth's orbit. So we have to detect these objects, project their orbits, and then figure out which ones could truly be a hazard to impact in the Earth because they come within 5 million miles of the Earth's orbit, and large enough to make it through the Earth's atmosphere and do damage at the surface. So we detect and track everything that we can find. But we find a lot of other interesting objects out there, and one of those objects is Bennu, the asteroid Bennu. Tom showed an image of it because we have right now a spacecraft at Bennu called the Cybers-Rex that is going to collect a sample off of the surface and bring it back to Earth here in a few more years. But Bennu is a potentially hazardous object. It has a small chance of impacting the Earth at sometime in the future. So the Osiris-Rex mission will tell us a lot about these objects and how we might be able to prevent a future impact. So the Planetary Defense Office at NASA, our whole strategy is, first of all, finding them. We can't do anything about them unless we find them. So a good deal of our effort is to detect, track, and characterize these objects so we understand what's out there and what we might be looking at. Then some of our effort is dedicated toward looking at plans for how we might deflect one from an impact trajectory, and planning what such a mission would be like. But as Tom alluded to, it's an international issue, so we have to be ready to coordinate that plan across not only the U.S. government, but other governments. And part of the work that we're doing with the United Nations is a precursor for being prepared to do those kinds of things. Then there's the mitigation. What are we actually going to do to deflect it, to protect human life and property here on Earth? And that involves both in-space activities, if we have enough warning and can get a spacecraft out to it fast enough, but also what would we do here on Earth? What are the terrestrial aspects of that? And we work with the emergency response community, FEMA in the United States, to plan those kinds of activities, to be prepared if one day we will find an object that is going to impact us in the near future. And then, of course, our capabilities to be able to assess how good we are doing. Are we finding them all? Do we know where they're going to impact? And if we do a deflection mission, are we successful in deflecting the object off of the Earth, as Tom's diagram showed? We don't want a bad deflection, we want a good deflection. So NASA's NEO search program, we have several current ground-based teams that are dedicated for every clear night searching the skies for near-Earth asteroids. The Catalina Sky Survey, run by the University of Arizona, is one of our primary teams. Also, the University of Hawaii runs several telescopes out on Haleakala and Mauna Kea in Hawaii. Another system in Hawaii, run by the University of Hawaii, is called ATLAS. ATLAS is smaller telescopes, but have a very wide field of view, so they try to cover the entire sky every night. They're not going to find asteroids that are far away and very dim, like these bigger telescopes are able to do. It's designed to find smaller asteroids that might be only a few tens of meters in size before the impact, several days to weeks before the impact. And then we work with the U.S. Air Force also on a project called Linear to use Air Force space surveillance assets to detect and track asteroids while they're doing their primary mission of tracking everything that's in Earth orbit. We only have one space-based system right now. It's a retired astrophysics mission, the Wide Area Infrared Survey Explorer, but we quickly, after it went into operation, determined that it could make a very good asteroid hunter because it operates in the infrared, where asteroids are much brighter and easier to detect. And also with infrared data, you can determine what the size of the object is quite rapidly. And so it's a better part of the spectrum to be tracking and detecting these objects, because the size and then determining what the mass is the most important parameter to know when we talk about what we're going to do to deflect one. So how are we doing in finding everything that's out there? This is the cumulative chart of all the objects that we've found over the years. NASA's program to do this, we've been doing this for quite a while, over 20 years now. Started in 1998. Our original charter was to find all the asteroids 1 kilometer and larger in size, because that would be a very bad day for all of us on Earth. It would cause the type of climate change that Tom talked about. Enough dust into Earth's atmosphere to wipe out the crops and cause mass starvation. So that was our first goal. But then the U.S. Congress in 2005 tasked NASA to find all the objects down to 140 meters in size. 140 meters, that sounds a little arbitrary. What is 140 meters? Well, it's about the size of, say, a high school football stadium. That chart that Tom showed you that showed those other two smaller asteroids, DA-14 and the Chelyabinsk object. Think of an object the entire size of that stadium, and then could think about the kind of damage an object that size could do if it were to hit somewhere in a United States or a European country. It would pretty much devastate that entire state or country, and that would be an existential threat to the United States. We would have difficulty economically and socially recovering from that large of an impact. So that's why that threshold is set. We for sure want to find all those objects of that size before they impact the Earth, and be able to have the time to do something about them before they impact us. Smaller sizes, yes, they're still dangerous if they hit a metropolitan area, but it's not going to end our way of life as we know it, so to speak. Currently in our catalog, we have a little over 20,000 near-Earth asteroids of all sizes discovered. And as you can see, about 2/3 of them are smaller than this threshold size that I talked about. But when we first find them, we don't know what the size is. We've got to track and characterize them to understand how big they are, so that takes a little while. So we track everything, we keep data on everything regardless of the size, so that we know if any of them could be an impact threat into the future. So how many objects are out there and how well are we doing on this? This is a chart that kind of shows our progress in finding the objects. The red curve is the estimated population of all the asteroids in these various size bins, all the way from at the lower right of the chart, you see 20 kilometers in size, all the way down to objects only 10 meters in size, which of course we don't need to worry about too much. On that population curve, you see marked where the Chelyabinsk object was, how big the Tunguska object was, and also some of our goals. The George E. Brown survey goal has us trying to find, by tasking from Congress, all the objects down to 140 meters in size. The green bars show the objects that we have found so far, and so you see objects larger than a kilometer or so in size. We have found most of those. In fact, we've found over 96% of them. But as we get down into the few hundred meter size, we still have quite a ways to go. This shows over the years the number of 140 meter and larger asteroids that we have found with our various systems. Back in 2018, we found 447 near-Earth asteroids of 140 meter and larger in size. This year so far, we found almost 200 now. In fact, I'm sure it is over 200 if this chart's a few days old. So that says, you know, we're finding at least one asteroid a day, and sometimes two. So every day is an asteroid day at NASA. Looking at this entire population, we think the entire population of 140 meter and larger is some 25,000 objects. We have found about 8,500 so far. So we still have about 2/3 of the population of these objects to find, even after 20 years of searching from ground-based systems. It's the current rate. It's going to take us about another 30 years to accomplish that if we are restricted to using just these ground-based capabilities. Close approaches to the Earth happen all the time. Tom has talked about some small objects that impacted the Earth, and so that was a very close approach. But larger objects come within the Earth and the Moon all the time. In fact, this shows all the close approaches within the distance of the Moon in the last year. There's about one a week. These, in the last year, there's about 6 of them there that came closer than the geosynchronous satellites. Thankfully, these are very small objects, only a few meters in size, so they would have disintegrated in Earth's atmosphere. A few of them are the size of the Tunguska object, between the size of Chelyabinsk and the Tunguska object that come between the Earth and the Moon just in the last year alone. And then there was 2 of them, shown here in the red, that were larger than the Tunguska object. So it is an ongoing threat, and these are just the ones that we saw and know about. The White House, we worked in the last several years in developing a strategy for the U.S. government for preparedness, and the White House last year, almost exactly a year ago, released a strategy and action plan for not only NASA but the entire U.S. government to improve our preparedness for detecting, tracking, characterizing the population, and developing technologies that if we find one, how would we deflect it, and also working our entire emergency response procedures and protocols for doing that. One part of that is enhancing our capabilities, and we're working on a space-based IR telescope to be able to do that. Currently, the program has enough funding to develop the telescope part of this mission to have it ready to be launched when some additional funds become available after we're able to do some more near-term things, which we'll talk about here a little bit more. So the space-based IR has the advantage of it's out in space. It can operate 24/7, and we can position it in an orbit that's more complementary in finding these objects. And complementary, I mean, to the ground-based capabilities, because the ground-based capabilities are looking out here and away from the sun because they have to look in the night sky. whereas if you're in space, you can look closer to the sun and see more of the population of near-Earth objects. Mitigation, what would we do if we found one far enough ahead of time? The National Academy of Sciences has looked at several capabilities and techniques and technologies and determined that there are probably 3 techniques that could be used. The most mature one is what we call a kinetic impactor deflection technique. We just hit it with a spacecraft hard and it changes its velocity and that changes its orbit. And so that's what we are going to initially pursue is a kinetic impactor capability. We also have techniques called a gravity tractor, where we just nestle up with a spacecraft next to it, and over time, nature's tug rope gravity will gradually pull that object off of an impact trajectory. And then there's, of course, a nuclear option, which isn't like it is in Armageddon at all. Let me tell you that. So they're waving at me in the back here, so let's get into talking about the kinetic impactor technique, and I'm actually not going to do that, but it's one of the, it is a mission that's sponsored by my office at NASA that we are currently working on. Elena is going to talk to you about that more. And so with that, I'd be happy to take any questions from you about NASA's program. No fair, Jim, you don't get to ask the questions.
We have one online question.
Oh, you have one on one. Okay, great.
Jacob wonders if you could give any information about the Lucy asteroid. He did not provide a number.
The Lucy asteroid. Well, let's see. I'm not sure that there's an asteroid called Lucy. Yeah, I don't think there's an asteroid called Lucy, but there is a mission called Lucy. The Lucy mission is currently under development. It will actually go out to the orbit of Jupiter and look at the asteroids that are what we call the Trojan asteroids that are in co-orbital with Jupiter around the sun. Next question.
Okay, well, thank you very much for this talk. Very interesting and enlightening. My question is, let's say that after a potential hazardous near-Earth object is detected, what are exactly the next steps? Is there a standing procedure? Or like you mentioned that you coordinated with countries and United Nations, but what is will be the exact steps?
Right. Well, first of all, as you said, we got to detect it. We got to know it's there. As soon as we detect an object that we think could be a potential hazard to the Earth, an alert goes out from our Minor Planet Center where this data is collected to get more observations on it. The first thing we've got to do is really nail down the orbit, determine where this object is and where it's headed. And then once we have a good orbit on it and understand where it's going to be in the future, then we can bring other assets to bear to characterize the object. How big is it? Is it really something we need to worry about? And if it is, what's its composition, and to get an estimate of what the mass is. So yes, there is this whole procedure that we have with astronomers around the world in other countries. It's all part of this international warning network that Tom mentioned that NASA is the leading participant in. And so we first of all determine if there really is a threat and how bad it could be. And then we start working on what we might do about it with not only in the U.S. government as the strategy document that I talked about, but also internationally with the Space Mission Planning and Advisory Group that we work with the United Nations. Another question?
You talked about ground-based detection, but I was wondering, the James Webb Telescope that's going up to replace Hubble, is it going to have any different capabilities to help discover asteroids?
Well, the James Webb Telescope is actually designed to explore the universe beyond the solar system. It's what we call an astrophysics mission. It's more of a classically designed telescope, and that it's designed to look very far away, but in a very narrow field of view. So it won't be able to see much of the sky at one time, and it'd be like looking through a soda straw trying to find all the asteroids. So it's really not well suited for this role. Now, once we find an object and need to get more detailed data on it, it is possible that James Webb Telescope could help us do that, but it would have to be in the right kind of an orbit. Jim?
We have another online question from Europe, and the question basically is, what made you passionate for this job that you have right now?
Okay, well, I've been interested in the space program since I can remember. I grew up during the Apollo era. I was in grade school during the Apollo missions. I always wanted to be part of the space program. But I was also interested in the Air Force, getting in the Air Force, serving my country. And I got into space surveillance, tracking everything that was in Earth orbit in my Air Force career. So I became kind of an expert in what they call space situational awareness. And so that prepared me. That's kind of a microcosm of what I'm doing now, tracking all the objects that are in Earth orbit and all the debris and determining if any could hit each other. And now I'm tracking planetary debris and determining whether any planetary debris could hit us and hurt us. So that's how I got my start. Okay, I think we're wrapped up, and with that, we're going to Lena.
Our final speaker is Elena Adams, who is the DART mission's systems engineer at the Johns Hopkins University Applied Physics Laboratory. Before that, she worked on NASA's Parker Solar Probe, the Europa Clipper, Van Allen probes, Juno, and ESA's ExoMars missions, as well as numerous studies for NASA and NOAA. She received her bachelor's in applied mathematics from the University of Virginia, a master's and PhD in space science, and a master's of engineering in space systems, all from the University of Michigan.
All right, as the last speaker, I'm going to keep it brief, but hopefully exciting, because this is a talk about the DART mission, which is the mission that we're going to do to try to go and move an asteroid. So Lindley showed this image, and it shows the Planetary Defense Office. You know, they assess, they search and track and detect, characterize. DART is definitely in the mitigate column. You can see us circled in yellow. So that's basically our mission. Go, hit a moon of an asteroid, create an impact, and kind of do the same thing as the asteroids do to Earth, which is basically now the Earth strikes back in an asteroid. So you can see that there are two objects in this picture, and it's the larger asteroid called Didymos, and we're going to be hitting the smaller one, which is a smaller moon that orbits the large asteroid. And I'll tell you in a minute why we're doing that instead of just hitting one big asteroid. So we're launching in 2021 in July, so that's just a couple of years away at this point. We're going to launch on the Falcon 9 rocket, SpaceX, and we're going to leave California really quickly, moving at a very high speed, because when we're impacting the asteroid, we're moving at something like 15,000 miles per hour. So leaving California, we stay in space about a year, and then in September of 2022, we hit the moon of Didymos. So we don't actually see the Didymos system at all until we're about 30 days away from the asteroid. And the first time we see the moon of the asteroid is about an hour before we hit it. And all of that is done completely autonomously. We're going to guide ourselves into this asteroid completely robotically. The ground's going to listen, you know, see that everything seems to be going okay, but the spacecraft is going to do all of its own thing. So it is pretty exciting. So what's the point of doing this? And how do we know anything about this object right now? So first things first, you know, let's talk about scales. How big is this asteroid that we're going to hit? So the bigger one, Didymos A, you know, we're very classy, you know, we call things A and B, just, you know, to simplify things. So the big one, Didymos A, is about 780 meters. And you can see it's somewhere between the World Trade Center and the Burj Khalifa. Now, the one that we're aiming for, the Didymos B, which is Didymoon, is about 163 meters in size. And Lindley spent some time talking about what's the size of an asteroid that actually, you know, presents a problem on a regional scale. You know, what would wipe out, you know, the state of Maryland? That's about the right size of the asteroid. So the reason why we chose it, why it's a very ideal asteroid, is because we can demonstrate that we can move this asteroid out of the way and make sure it doesn't hit Earth. Now, Didymos in no way, shape, or form is going to hit Earth. it's actually locked. The system is locked. So when we move Didymos, the little moon, it's just going to speed it up. So what we can do from the ground is we can observe how the brightness of that asteroid changes, and then we're able to actually tell how much we moved it. So this is a really good way of demonstrating an impactor technique. Now, how big, before I move on, how big is our spacecraft that's going to do that? We're about the size of a school bus with our solar arrays. So what do we know, and how do we know anything about this Didymos system? So what you're seeing here is the best knowledge we have of the Didymos itself. And Didymos was discovered in 1996. Then it had a it came closer to Earth, about 5.6 million miles, I believe, or 5.9 million miles, where we were able to use the radar and basically image the asteroid. And we've done a lot of the observations from the ground. It comes around every couple of years, and we do more observations. What you see down there is a little moving dot that's streaking across the sky very slowly. That's how we see Didymos right now. We also look at it, and we look at it with the optical telescope. So this right here was done with an 8-meter, very large telescope. And from there, we can tell how big the size of the object is. What we also are seeing is the brightness of the object. And every, let's say, 12 hours, there's going to be a dip in the light of the brightness of the object. And that's how we know that there is a moon around that object. So we see a 10% dip in the light, and that's how we know that Didymos B has crossed the path of Didymos A. And we're trying to hit that object that's just doing the crossing. It's pretty exciting. So this picture was already shown by Tom earlier, but basically what you can see is our spacecraft moving in will change the orbit of the of the moon by about 10 minutes. And then after we hit the asteroid, the ground-based observers will get their field day and spend a couple of months watching the brightness change and basically being able to tell how big of an impact we were able to make. Now, how do you know how big of an impact we're going to make? Well, it depends, right? It depends on the size of the spacecraft that you hit it with, right? The more massive the spacecraft is, the bigger impact you're going to have. And also, how fast it's moving. If it's moving faster and it's a bigger spacecraft, you can move it farther along. So our spacecraft is about 700 kilos, which is about the size of a cow. And we're moving at 15,000 miles an hour. Also, we're pretty close to Earth at that point, at 6.8 million miles from Earth. And we're trying to hit an object that's about 500 feet. So just think of that. Very fun, very fun. We love our job. Okay, DART spacecraft. This is how our spacecraft actually looks like. It's a box. It's about 9 feet by 6 feet, so I'm 6 feet tall. The spacecraft's about my height. What you see on the spacecraft is our main camera. It's called Draco, and that's what's going to guide us optically into the moon. And what you also see are these giant solar arrays. Not only are we demonstrating the technology for the Planetary Defense Office that we can move an asteroid, what else we're doing is we're demonstrating other technology for NASA to basically move the technology forward. So we have these rollout solar arrays that look like blankets. We also have a little CubeSat called LiCiCube, and they're from our partners in ASI, which is the Italian Space Agency. And what this CubeSat is going to do, after we slam the asteroid, they're going to fly by 5 minutes later and take images of the impact ejector. So you saw, impact craters, you have a lot of plumes coming out. And that is exactly what they're going to take a picture of. So basically, it's our selfie camera. And let's see, what else we're demonstrating? We're demonstrating the NEXI ion thruster, which is going to propel us to the asteroid as well. And I'm just going to say that the last 4 hours of the mission are going to be extremely exciting for us. You can see that the spacecraft is, Earth is to the left, the sun is on top. Oh, here comes the asteroids real fast. really, our goal of the mission is to be able to not only move the asteroid, but also send some images back before we impact. So in the last minute, we're going to be taking a lot of the images, and then we have a requirement on us that in the last 20 seconds, we need to be able to send at least 2 pictures back, streaming them 6.5 million miles to Earth before we impact, because once we impact, those pictures not going anywhere. So it's a very fun job to try to orient ourselves that we're able to stream images back, video basically back, and hit the asteroid. So I will just point out, we're in our process. We're actually in the process of building the spacecraft at this point. We had a big milestone recently, which means that we're now okay to go ahead and fabricate our spacecraft. And we have a launch vehicle. So in a couple of years, we're going to launch, and the year after that, hitting an asteroid. Thank you.
Online question.
Okay. If anybody has any questions.
We do have one online question.
Okay.
You are basically the real Star Wars lady.
Yeah, basically.
Yes. What are statistically the chance to have one of those big things hitting Earth?
That is a really great question, and I wish I could just throw it over to Lindley for that to happen. But the 160 meter is not very likely, right, Lindley?
Of this asteroid?
Yeah, the 160 meter chance.
Of this asteroid or any asteroid?
Any asteroid?
There's no chance that this asteroid.
This one seems to be the one you've detected.
Oh, yeah, no, so this the chances of this asteroid hitting Earth is pretty much none. And there's no way for us to knock the moon out of its orbit around the asteroid. The reason actually why we chose having going to a binary system, so having a moon and a larger asteroid instead of just hitting an asteroid, is to A, ensure that there was no way that's going to come back to bite us. And then B, is also we can really measure how much we move the asteroid because we can observe its change in the rotation period. Go ahead.
We have another online question. Urbane asks, and I'll try and summarize here, since Department of Defense and Congress and the White House are now talking about the Space Force, does that have implications for planetary defense and for you specifically the DART effort? Is there anything in all of this talk of the Space Force about planetary defense?
To be honest, I don't really know what Space Force is doing. However, Lindley does, and he'll talk about that.
Why don't you go to the mic?
You can turn mine
In the
on.
meantime, I'll just say that DART is ready to go even without Space Force.
Yeah. Okay. Well, the talk about the Space Force. That is a Department of Defense organization and capability. It's all about military capabilities for protection of our space capabilities, knowing what's going on in Earth orbit, and defending our capabilities in space. It has nothing to do with NASA, the civilian space program, or planetary defense.
The answer is, I don't know how many of you heard, but the answer is no, but we're very excited that they'll be working with us. Any other questions? We're good?
Yes, we do.
Oh, okay, sounds great.
Hi, I just wondered, when you said the asteroids won't hit the moon, how far do you track the future path of that asteroid, and how do you know that it's not going to have ramifications further on into space?
So we are planning to track, so we have funding to track it for at least 3 months after, and we already have a lot of the ground telescopes lined up to look at the asteroid and make sure that the change that we imported is measurable. And then after that, the astronomers track these things all the time. So during any time these asteroids come close to Earth, they do track them. So as I said, Didymos comes by every couple of years, and at the closest approach, our ground-based assets do look at it.
Okay, thank you.
Thank you. All right, I think that's all with the questions, and now I think we're opening up for the general public.
Yes, that's all of the presentation. So now all of the speakers. All of the speakers will come back up on the stage and we'll answer additional questions here. We can still get online ones. Please bear with us in sort of shuttling it to me to then to the speakers. But the rest of our time remaining is for additional questions. Please go to the mic for those of you here in the audience, just so everybody can hear.
Exhaust all questions yet?
Anybody got any questions? Go ahead.
Hi, just for you the question. What are the kind of tests that you run so that you can assure that the mission will be successful?
Oh, yeah, that's a really good question. There are a lot of tests that we run. So where do I even start? So part of the building of the spacecraft, you spend at least a year in test. And for us to test that, to ensure that we hit the asteroid, there are a lot of simulations that we do. So what we have is a system where we're basically feeding video stream into our spacecraft, and we are using our guidance system to target ourselves in it. And then once we're in flight, we're going to be observing actually the Jovian moons and watching them transit behind Jupiter. And we're going to be guiding ourselves to the smaller moons to ensure that we can hit. And then in addition, there's a variety of other things that we do too. So I'll just keep it short. Go ahead.
This question is for Mr. Lindley. Once you hit an asteroid with your, what do you call that, static?
Kinetic.
Kinetic.
Yeah.
And the asteroid, you hit it first and then takes another direction. What if it turns in another circumference around the Earth and comes back to hit the Earth? What's the contingency plan? Is that when you hit it with a nuclear?
Yeah. Well, in the instance of DART, we've selected an asteroid, first of all, that is not any danger of impacting the Earth in the future. And the reason we're hitting the moon is that it just changes the orbit of the moon about the primary asteroid. It doesn't change the orbit of that system around the sun. So it doesn't endanger the Earth any more than it is right now from that asteroid. So it's a very nice laboratory that nature has set up for us to do this kinetic impactor test.
Can I add something too? Anytime we deflect a future asteroid, one of our challenges is to track it, predict where it might strike the Earth. But then if we're going to design a deflection mission like the DART one, for example, you want to design the impact so that it doesn't divert the asteroid on a subsequent orbit around the sun back to strike the Earth. And that's a fundamental challenge that we are going to take great care of. So we're going to strike the asteroid in such a way that it can't come back and hit us on a subsequent revolution. And that's all about the targeting, the precise targeting that Lena's team is designing for the DART mission. Okay, so, and then there's the ground tracking that will occur that will guarantee that the results planned were the results delivered. And if it were to go awry, then you would launch another deflection mission. And in fact, we talk about these things as deflection campaigns, where multiple spacecraft will be sent to divert an object. In case one fails, then you have a backup spacecraft to correct the course.
That whole sector of assess on my strategy chart, the planetary defense strategy chart, is what this is all about. You know, assessing what the effects would be from what we do. Our current capabilities on modeling the orbits of these asteroids, given enough observations, we can predict the orbits well into the future, a century or 2 centuries into the future as to where these objects are going to be. And that's how we can determine that an asteroid might impact the Earth someday into the future. But we can know when that day is. Once we detect the asteroid and determine its orbit, we can determine if there is any possibility of impacting the Earth and what that day will be into the future, even a century into the future.
Oh, and I'll jump in too, just because it seems like everybody's jumping in.
Yeah.
But The other piece of it is that you want to nudge the asteroid, but you don't want to break it up. So you have to hit it with just enough force to move it, but you don't want to hit it with so much force that you break it up and those pieces come to Earth. So it's a very delicate balance because you have to live in that sweet spot, and you have to really understand what the asteroid is made out of in order to be able to do that safely.
It's a huge modeling exercise. That's what it really is. It's all done with math.
Yeah.
Hollywood wants to blow things up. That is not the way to do it.
Yeah.
Thank you.
Thanks.
Not fair, you can't answer your question.
Well, I know we've been talking about mitigation, but I know you've also done a lot on disaster preparedness. Should anything actually impact Earth, whether it's something we found and couldn't move, or something we found too late and you couldn't move. So, Mike, tell the folks on what you've done in disaster preparedness.
This is my wife, Randy. That's why I told her she couldn't ask a question. But she wanted me to talk about. We have done several exercises over the last few years with FEMA and other government agencies to ferret out all of the problems and issues that might come up if we were to detect an impacting asteroid, what we would do about it, how we would assess things, how we would advise leadership on what the options might be. And so that's a continuing thing that we do within the U.S. Government and with our international colleagues as well. We're starting exercise efforts with the international community in this area.
And then, so you predicted in the next 30 years that you were able to track all the near-Earth objects. What do you base that upon?
I missed the last part of your question.
All the near-Earth objects. You said it was like 30 years you'd be able to.
Well, it's going to take us another 30 years to find what we think is the rest of the population of 140 meter and larger. That's not all the population, but it's all the ones that we think we need to seriously worry about.
Thank you.
We have one online question, and it's sort of directed to everyone. And if I understand the question right, it's thank you for the presentations, but do you have any words specifically for Europe, the European people who are watching this, and Hera in particular? I assume that's the person asking. And the part of the question is just what stimulated the interest in asteroids from all of you?
You want to do the Hera one first, and then we'll come back?
Sure, let's do the Hera one. So we're hoping, so when the DART mission got started, it was actually part of an international effort where it was going to be a sister and a brother spacecraft that were going to come together. DART was going to hit the asteroid, and then AIM from Europe was going to fly and actually measure how much impact we were going to have and measure how much ejector we were going to have and what exactly the effects of this impact were. But then the European spacecraft got canceled, but over time it got involved into Hera, which is the mission that Europe is in the process of selecting right now. And that is going to come, I think maybe 4 years after in 26, and is going to arrive, and it'll have also CubeSats that are going to come closer to the Dynamos than we are, and it's going to look at the impact crater and the impact effects that we have had on the Dynamos system.
Even though the ESA mission is going to arrive after the impact now instead of before, it will still provide us a lot of valuable information about what the effect was on the system, how big the crater was made by your little school bus size spacecraft, and more precisely measure the new orbital period of the moon. We can measure it well enough from ground-based observatories, but having a spacecraft right there with the system will give us a much more precise measure of the effects that we've had.
Yeah. We're very excited about the mission.
I think there was a question about how we got involved with asteroids. I think I kind of answered mine already. That I've been involved in the space program for quite a while, and looking at now planetary debris as opposed to just satellite debris.
It's my first asteroid mission. I mainly worked on the outer planets, actually, and on the planet Earth. And I'm actually really excited. As a technology demonstrator, you don't get to hang out with the scientists as much. But on the other hand, you get to demonstrate a lot of really cool technology. So I'm a fan.
Oh, we've made an asteroid hunter out of her.
Yeah, we did.
I was looking at how I could improve my education so I could become an astronaut one day. So I needed more science education, and I decided to go study planetary science. Thought I would be studying Mars exploration as part of the future of human spaceflight. But when I got to graduate school at the University of Arizona, I met some very inspiring scientists. My PhD advisor was a guy who was interested in space resources from asteroids and the moon, how you could use the materials out in space to lower the cost of space exploration and to increase the wealth of the planet by using the resources out there in our solar system. So I started to learn more about asteroids in regards to that. Then I used telescopes to study them to learn whether there was water on some of the main belt asteroids between Mars and Jupiter, water being more valuable than gold out there in space away from our Earth. So that's how I got interested in the physics and the composition and the history of asteroids. And then I think it's just a natural transition. The more you know about them, the more you discover that we can use them beneficially, and we can also use our space skills to prevent them from being a problem in the future.
You just answered part of my question, but what I was wondering is what kind of education and background do people have that are getting involved with these missions as like an entry level? Like, what are you guys looking for?
Future candidates for this field, boy, we could use, we need enthusiasm, we need skills, we need volunteers, we need smarts to help us prevent a future asteroid impact. So in planetary defense, you know, it takes engineers, it takes astronomers, it takes planetary scientists, geologists to understand the makeup of the asteroids, and physicists to help us predict the impact effects were one to strike the Earth. So it's a very broad field with lots of interesting people working in it right now. You know, all three of us were at a conference last month in College Park across town where the global community of experts on planetary defense got together. What an exciting group of folks to be a part of.
Well, I also want to point out that you know, you don't have to be a scientist or engineer, mathematician to be involved with this. You know, NASA requires all kinds of skills to do all the various aspects of what we're doing. As Tom says, it takes a team, and we, you know, employ journalists, people with journalism background. We have a lot of public affairs interaction with the media, and so we need folks that have journalism background, folks that are working IT, you know, systems, working computers. Although the administration field isn't as big as it used to be because they all give us these computers now to do our own admin work, but we, you know, still have administrators, people that run our offices and keep the offices rolling smoothly along. So it takes people of all skills to be a space program. So you don't have to be a brilliant scientist to be part of the space effort.
There's an online question that's sort of a follow-on, and that's how many women are involved specifically in missions, but also just in what you're doing, Lindley, and what can we do to encourage more women to participate?
So I'll just answer for DART. Our engineering lead team for, you know, we have various subsystems, you know, we have the spacecraft, we have the ground, we have mission operations, it's about 40% women. So that's a pretty high number for a STEM field. Usually, you know, you're seeing the 20% kind of number. I don't mind. It's kind of nice. I like the balancing. I think the way to encourage more women in these fields is to have more women in these fields, and I like it. Go team.
I think planetary science in general has fairly high percentages of women. There's a lot of women that I work with at the Planetary Science Division. You know, half my staff in the Planetary Defense Coordination Office are women. So I think this field, you know, first of all, I think it sparks some fundamental interest from all humans, not just men. You know, what is our solar system? What is our future in the solar system? So I think, you know, although that might not have been true 20 years ago, there's certainly been a growth of women in planetary science and exploring the solar system, which I think is a very good thing, because they bring I could tell you, they bring an entirely different perspective to everything, which is valuable to our overall efforts.
Yeah, just like we were saying earlier, where it's, you know, global, but it's also just human. So I don't think gender really matters in the planetary defense exploration kind of sense.
No, it doesn't.
Let me add, in terms of women in planetary science, Ellen had another appointment, so I'm here if there are any sort of cratering questions. But she is a good example of what you just said. She started in planetary science. When I began in planetary science, there were a lot of women. I think that is a great way for women to be exposed to the potential.
Well, first of all, thank you for your work and thank you for your presentation today. My question is, if there were to be an asteroid strike tonight, and now we got a fresh new impact crater to study, in what ways would that advance your knowledge, or what would that allow you to do as opposed to studying million-year-old craters?
That's you.
Impact crater question, I think we're throwing it over to you.
Let me just say it depends a bit on how big the strike is that you're talking about.
Yeah, I hope it's not too big and it's in a remote location.
That's the optimum, but as one of Tom's slides of the fireballs, they're happening everywhere, and unfortunately we have zero control over that, so we need to be prepared for all of those ranges. Anytime we have an impact, it is a natural experiment, and we will learn. There was an online question that happened while we were just discussing, what if there was an impact on the moon, and would that affect us? That's kind of related to what you're talking about. We learn from any of these that we can observe. When we have spacecraft specifically sent to observe, in DART's case, making the impact itself, we're going to learn things that we just hadn't even thought of. So carrying out experiments is an important part of understanding what we need to do. DART is just the beginning of what I hope will be a long line of experiments. Nature provides these impactors on a non-scheduled basis, and we just need to be able to be instrumented enough around the planet. When it happens, we have the data that will teach us something.
Yeah, but having a controlled experiment is key. So you know exactly what you put in and what you got out, because, you know, nature doesn't really provide that so well.
Yeah, ideally, you know, we would be able to find that object, if it were a national impact, find it, you know, several weeks to months ahead of time, so we've got some time to characterize it with our telescopes and other observing equipment, so we understand what the object is that's going to impact us. Hopefully by then we know where it's going to impact, and chances are that's going to be in a remote area, because urban areas, as Tom said, are less than 4% of the Earth's surface. And so, you know, could be a very controlled experiment from that aspect. So another good reason to, and we continuously monitor the skies to find anything that's going to impact the Earth. Not only the Earth, though, our Center for NEO Studies calculates whether it's going to impact the Moon or Mars or any of the other planets as well. It's all done with the same modeling that they do for Earth, protecting the Earth.
While we're waiting for the next question here, I'll mention that amateur astronomers are now readily collecting data about impacts on the Moon. I subscribe to a magazine called Sky and Telescope. There was a recent article of people who use video when filming during a total lunar eclipse, and we found several impacts that were recorded by these amateurs. They weren't professionals. So we're learning all the time.
Yeah.
Hi. Earth is this huge astronomical body, and you know, being in space, you kind of have like an interesting perspective on like how small or large that we are. The question is like how like climate change can, how can individuals who can't see climate change as I guess, the size of Earth?
Well, I have a reaction to your question.
Yeah.
You know, climate change is a problem that we all face together. It's another international hazard or challenge, and we're going to solve it by cooperation. Climate change is a very difficult problem because the climate's already changing naturally all the time. We have a contribution. We have to figure out how to switch our energy sources to clean sources of energy for a growing population. That's a really tricky problem, and I don't know the answers to it. But planetary defense is a problem with pretty straightforward physics in terms of predicting the orbits of asteroids, determining where they might strike the Earth and when, and then the physics of actually stopping that process from occurring are also fairly straightforward in terms of the physics. Now, executing it is very complex, building the machines that are reliable enough, building the predictive capability, and so on, and actually negotiating how to do these jobs of planetary defense across international borders. That's a challenge as well. But it's a lot less complex, I think, than climate change. And so, in a real sense, we're changing the way the solar system operates to protect our planet, to protect our species. And that's a really good thing, that we're changing the way the solar system operates for the first time in 4.5 billion years of solar system history. And we have those tools, and we, I think, can handle this problem. There's been a lot of international cooperation over the last 20 years at the UN and between the space agencies that is very encouraging. And I think if nature gives us enough time between now and the time we face a really damaging prospect of an impact, we're going to have the plan worked out in advance, just like a spacecraft or an astronaut's checklist. We'll have that plan worked out in advance and on the shelf to know what spacecraft to build, how soon we have to launch it, which countries will cooperate, and how we'll agree to carry out that mission and fund it. And that's the challenge, but it's also encouraging that it's a problem that we can actually take on with the skills that we have today. So we're not going to just be helpless victims of this natural process of cosmic bombardment. Now we're going to take control of our fate in terms of this space hazard.
We have another online question that gets to the question of tools. And you mentioned certain Earth-based resources. The question is, how are the locations of our Earth-based observatories, like those in Hawaii and elsewhere, chosen? And I would add, how might we choose better ones specifically for planetary protection?
Planetary defense or planetary protection?
Defense, that's what
planetary defense, yeah. Planetary protection is another area of investigation. That's to prevent biological cross-contamination between planets. All of our spacecraft have to go through decontamination procedures before we launch them so that we don't spread ourselves across the solar system unintentionally. That's planetary protection. Planetary defense, ground-based astronomical assets are chosen by a very careful process on finding good sites to observe from the Earth. Now, most of our telescopes are optical telescopes. They, have mirrors and lenses and operate in the optical bands. And so we need to get them as high up in the atmosphere as we can, because the Earth's atmosphere, heat and disturbance in the atmosphere distorts the image that they are able to collect. So we get them as high in the atmosphere as we can in the driest environment that we can, and it just so happens Hawaii, the volcanic mountains on Hawaii, and some of the mountains in the southwest United States provide the best locations for optical telescopes. Now, what we'd really like to do is get up above all of that with a space-based telescope and that could operate 24/7. It doesn't have to deal with the day or night cycle, doesn't have to deal with weather, so that we could hunt 24 hours a day, 7 days a week, and a continuous capability. It's not attenuated from the atmosphere, and we could operate in the infrared part of the spectrum as well. Under the Earth's atmosphere, all that water in the Earth's atmosphere absorbs the IR part of the spectrum, whereas we get up above all that, we can hunt for them in the IR, and there we're detecting the heat from the sun on those asteroids. The asteroids absorbs the sun's heat, and it re-radiates it, and we see their heat signature which causes them to stand out from the background of stars and also gives us a good idea of what their size are, because the heat signature is proportional to the size of the asteroid.
That answer is leading into another online question. This is from Eric, and it has to do with what is sort of the main limiting factor in discovering these new asteroids. What is the technological piece that is the weakest link?
I really think that, I really do think that what Lindley said about the infrared is really the key piece, because we cannot do very much with infrared from Earth. And but visible telescopes in space can help too to look for these asteroids. In addition, you know, you're basically talking about covering the whole sky. That's a lot of data to bring down. That's a lot of data to process, because what you're doing is you basically are saying from, you know, from night to night, I'm watching this one area and the asteroid is the thing that moved a little bit, right? I know the stars are moving this way, but the asteroid has, you know, because you're searching for this pattern, you're searching for this one little asteroid that has moved just a little bit, so to discover new ones, right? So it's a massive cataloging problem, because you have to make sure that this is the piece that moved, and it's a new one, right? You want to look through your whole catalog of, you know, 20,000 objects and say, this is not the same one that we already have cataloged and we know exactly what this thing is, right? You want to be able to say that this is a new one. So from my perspective, it's this massive data conglomeration that's the big piece. But NASA is already doing a lot of that. However, if we have more things online, you know, it's a harder data fusion problem.
I think one of the limitations, if you want to call it that, is that a lot of these objects go out beyond the orbit of Mars. A lot of them originate from the main belt of asteroids between Mars and Jupiter. So the orbits take them out that far, and you know, 100-meter, even a kilometer-sized asteroid at that distance is extremely dim. Finding a 100-meter asteroid beyond the orbit of the Moon, you know, somewhere between Earth and Mars, it's like hunting for a candle at the distance of the Moon. That's the kind of dimness that we're talking about here. So you've got to have a very capable telescope. You've got to survey the whole sky, because they can be anywhere in the sky. As Lena says, but you can't look too close to the sun from the ground, or from a space-based capability, because the sun is so bright, and it would burn your optics. So it's an engineering challenge, even hunting for them from a space-based capability.
I'll add, there's one more online question they must be following real time here.
Must be listening to us, huh?
What telescope is going to replace the one that's in orbit? And I bet the question is dealing with Hubble. So James Webb is a very large telescope that NASA will launch fairly soon, but that's different than what these guys are discussing. So maybe they can elaborate on the differences between large space-based for astrophysics as opposed to what they're discussing.
Yeah, well, as I said before, somebody asked a question about James Webb, and it's designed to look beyond the solar system and study the cosmos, astrophysics, as we call it, planetary systems and around other stars and even other galaxies. I think the question may have been, talked about WISE and NEOWISE that we're currently using. That spacecraft is far beyond its designed lifetime, and in fact we expect it to die, so to speak, here in the next year or two, and so we won't have any space-based capabilities for detecting and tracking these objects. So we are designing a space-based IR telescope specifically designed to detect, track, and characterize asteroids. Have that on a development path. It's awaiting some additional funding for us to be able to accelerate that program, but we are on a path that it could be launched in the second half of this next decade with the current funding levels. We'd like to do it a little faster than that, but we've got DART to do first, right?
Yep. Just a few years to go, though.
Lindley can't say this, but I can because I don't work for NASA anymore. And so that, the NASA budget is about $21 billion a year, and this infrared space telescope, NEOCAM, that he's talking about is 1% of the NASA budget in rough numbers, okay? So it's a tiny fraction of the NASA budget. All of you folks who live in the US can call your congressmen and senators and say, we ought to bump that number up for the NEOCAM and get that online a little bit faster. So that's my commercial for how you can help us with planetary defense.
We're about out of time, so one more question here, and then I have one final online question.
Okay. How long can somebody last in space without a spacesuit, without exploding or whatever happens? And have you, Mr. Jones, have you been on the moon?
Okay, so that's my question. Yeah, astronauts will take those questions. So I haven't been on the moon. The Apollo astronauts are my heroes when I was growing up. That's how I got inspired to become a space scientist and then an astronaut. And I've been on spacewalks at the International Space Station, and I wore a spacesuit. And so I was in a bubble of oxygen held in by the spacesuit surrounding me so I could breathe and so I could keep myself from swelling up in the vacuum out there. So yeah, if you were exposed to the vacuum of space just like I am right now, within tens of seconds, the fluids in the tissues in my body would start to boil, and the swelling that would result from that would quickly asphyxiate me. I'd die of asphyxiation very quickly. Now, that's forgetting about the thermal extremes from the solar radiation hitting you and the freezing on the dark side of your body that would afflict you as well. So there's lots of ways to die in space. The quickest one would be the lack of oxygen. You would asphyxiate very quickly.
So just a couple of seconds.
I could maybe bring you back from 20 seconds of that if I got you back inside very quickly. Okay. Let's take the positive side of it.
Thank you.
And our final question will be online, and it's for Tom. Can you see meteor showers while you're in space? That's actually an interesting
That's a fun question, yes. So I've been lucky enough to look down on the Earth as often as I could in space in the 53 days I was up there. And it's striking to see a shooting star below you. A tiny grain of sand, maybe something the size of a pea, hurtling into the atmosphere at 15 kilometers per second. And of course, it gets incinerated by friction with the atmosphere and flares into what we call a meteor. That's that flash of light that you see looking up or looking down. And so when you think about seeing a shooting star below you, a meteor below you, it reminds you that you're bathed in the same swarm of asteroid and comet debris zipping around, let alone space junk from man-made objects. All of that is what presents a hazard to your spaceship. So it's both very beautiful, but it's also a reminder of, hey, there's a hazard up here that we have to design our spaceships for.
And with that, we are running out of time. I think we should thank our panelists again, and thank you to the audience.
Thanks for coming.
And enjoy the rest of your day here at the museum, but also pay attention to Asteroid Day.